So the strength of those intermolecular forces depends on the specific particles involved. And the state of the matter depends on the strength of the intermolecular forces. So if we have strong forces, then we have high melting and high boiling points. If the Velcro holding things together is really, really strong, it's going to take more energy, more movement to break loose from it. Does that make sense? This is some of that part of chemistry where you kind of have to be able to just think about it. And if you can think about it in relationship to real life, it actually makes some sense, and then it's so much easier to remember. If the forces are weak, it will melt at a low boiling point. It'll melt at a low boiling point. That makes no sense. It will melt at a low temperature. It'll boil at a low temperature. If the Velcro is weak, then it's very easy to move those particles apart from each other. It doesn't take much energy at all. High temperature is higher energy. So those particles have charges, partial charges, temporary charges. That is what gives rise to the intermolecular forces. So we have to revisit Coulomb's law. Here's the whole version of Coulomb's law. What we're interested in is that the potential energy of two charged particles, Q1 is the charge of one and Q2 is the charge of the other, is going to decrease. It's going to become more negative with increasing magnitude of charge and decreasing separation. R is the separation between the two particles. These have to be oppositely charged to attract. Remember, negative energy is good. Things are trying to go to a lower energy. And so negative energy represents that the particles are attracted to each other. It will become more negative as Q1, if Q1 and Q2 are larger, if you have larger charges, or if the distance between them is smaller. So the force of attraction is greatest when the particles are close together and when the magnitudes of the charges are larger. So more charge, more attraction. There's bonding, which we've talked about. So here's a water molecule. We have a covalent bond between the oxygen atom and the hydrogen atom. And this involves large charges of the protons and the electrons at very close distances. The distance of this bond, the length of the bond, is 96 picometers. The intermolecular forces happen between the molecules. And the distances here are significantly larger. So perhaps 300 picometers in distance between the two particles that are experiencing forces of attraction. The distance is really important, and I've mentioned this before, but you take a magnet on your kitchen refrigerator and you put a piece of paper up there. It's fine. You put two pieces of paper under the magnet. It's fine. But as you keep adding pieces of paper, it doesn't take very many pieces of paper before the magnet won't stick anymore. And those are very small changes in distance between the magnet and the refrigerator. And so small changes in distance between these oppositely charged particles have a big impact on the strength of the attraction between them. So intermolecular forces are much weaker than chemical bonds. We're going to talk about, I think, 4, actually, intermolecular forces. The first one is called a dispersion force. This one actually also has a lot of other names, sometimes called a London force, London dispersion force, van der Waals force, induced dipoles, all names for the same thing. This dispersion force is present in all substances, all molecules, all atoms. Everything has this. And it is a result of fluctuations in the electron distribution within a molecule or within an atom. So if we look at a particular atom and we take pictures of it at different times. Here are the 2 electrons. So this is helium. There's 2 electrons, and we take a picture here. We take a picture here. Remember, we can't predict or describe exactly where the electrons are moving. We can know the velocity or the position, not both. So here we're looking at the position. And then this one, they happen to be both on the same side of the atom. Could it happen? Yes, it could. This reminds me of the time when I walked into the living room and all 6 of my children were on half of the couch. Usually they're just scattered all over the place, and now they're scattered all over the state, right? But all 6 of them on the couch together looking at something. I took a picture. Like, I've never seen that happen before. So this maybe doesn't happen very frequently that the electrons happen to be on one side, but it can happen, right? They're just sort of randomly distributed, and they can end up on the same side. When they end up on the same side of the atom, there's a charge imbalance. We've got the 2 electrons over here, and the protons are there, and there's nothing on this side to balance charge. And so we have a dipole moment in this atom. It doesn't last very long because these electrons are moving around. The kids didn't stay on the couch very long, but they were there for like a minute, and then it was over. So we have a partial negative charge on this side of the atom and a partial positive on that side of the atom, and it happens spontaneously. It doesn't last very long, but it can happen. It's called an instantaneous dipole or a temporary dipole. It doesn't stay. But what it can do is it can induce a dipole in a neighboring atom. So if you have this spontaneous dipole in this atom where you have a partial negative here and a partial positive here, and here you have an atom nearby, this partial positive charge is going to attract the electrons of that atom and induce it to be unbalanced as well. And so now this one has a negative, partial negative, and a partial positive charge, and there is a force of attraction between those, and that's the dispersion force. The attraction between instantaneous dipoles in neighboring atoms. This one induces a dipole in the next one, and then there's this interaction, this attraction between the atoms. This one had the initial instantaneous dipole. It came, it went, and when that's gone, this one goes and that one goes. And so these are attractions that come and go. But little tiny bits like that can add up. It rained the other day. Were any of those raindrops huge? No, little tiny raindrops. But you get enough of them, and they add up to a significant amount of water, right? So these instantaneous dipoles, these attractions are very small, and they don't last very long, but they happen over and over again, so they do add up. The magnitude of them depends on how easily the electrons can move in a molecule or an atom, how easily it can be polarized. So there is a trend here. We see that a larger electron cloud is easier to polarize. The electrons are held less tightly by the nucleus in a large atom. Those outer electrons are farther from the nucleus. They're easier to push around. And so we see that the dispersion force will generally increase with molar mass. The larger the atom is, the more easy it is to get it out of balance and have an instantaneous dipole. So we can observe this by looking at the boiling points of substances. So if we look at the noble gases and we look at their boiling points, helium exists as a liquid below 4.2 Kelvin. That is really close to absolute zero. That's mind-bogglingly cold. So that boils at 4.2, neon boils at 27, argon at 87, krypton at 120, xenon at 165. What is the only difference between these noble gases? Their size. Xenon is a larger atom. It is more easily polarized, and so these dispersion forces are stronger. The force is stronger with xenon because it's more easily polarized. And we observe that in the higher boiling point. To get xenon to boil, you have to get to a higher temperature. Higher temperature is more kinetic energy. It takes more kinetic energy for the xenon atoms to break loose from the Velcro. Higher boiling point, stronger intermolecular forces. Does that make sense? Any questions? Molecular shape matters as well. If we look at these two substances, these are both pentane. They've got 5 carbons. This is normal pentane, where the carbons are arranged in a line, and this is neopentane, where 4 of the carbons are all attached to a central carbon atom. This causes a difference in the shape of the molecule. The molecules have the same molar mass, they have the same size, but they have different shapes. So normal pentane is more linear in shape, and neopentane is more spherical in shape. So if we think of these molecules as being covered in Velcro, this more linear molecule is going to have more surface area to come in contact with another one. And so it makes sense to me that with this larger area for interaction, the intermolecular forces are stronger, and I would expect N-pentane, normal pentane, to have a higher boiling point than this one. This one's spherical, and they can only touch at a tiny, tiny point. The area where their intermolecular forces can interact is much smaller. And so we would expect this to have a lower boiling point. So if we're comparing similar elements or compounds, molar mass is a useful guide. But if the molar mass is similar, then we need to look at the shape. Well, there should be a thing that tells us the temperature. Oh well, there isn't. That's dispersion forces. Another force is called the dipole-dipole force. This exists in all polar molecules. This is stronger than a dispersion force. And this is, it is stronger because polar molecules have permanent dipoles. This isn't a force of attraction between dipoles. But unlike the dispersion forces where the dipoles came and went, here the dipoles always exist. These are polar molecules, the dipole's always present, and we get this constant attraction between the dipoles. So if we look at, what are we looking at here? 1, 2, yeah, you don't care about the name of it anyway. 2 molecules. This is a polar molecule. We've got the oxygen up here, and we've got the carbons and hydrogens down here. And so we have a partial negative and a partial positive charge. And it's always that way. It's a polar molecule. And so there's an attraction between the negative end of one molecule and the positive end of another. Here's the electrostatic potential map, looking at the electrons. So there's increased electron charge or charge density here and decreased there, and so there's a force of attraction between them. Polar molecules also have the dispersion forces, but they have the dipole-dipole forces on top. And so we see that the polar molecules have higher melting and boiling points than nonpolar molecules with similar size. So if we look at formaldehyde and ethane, their molar masses are almost identical. That tells us that they're similar in size. We look at their structures, and this is very symmetrical, and so we would expect this to be nonpolar, and it is. And we look at this one, and even my rule of thumb predicts that this is going to be a polar molecule. The carbon doesn't have any lone pairs, but the oxygen is different than the hydrogens. This is lopsided. It's a polar molecule. When we look at the boiling points and melting points, formaldehyde boils at minus 19. Ethane boils at minus 88. So ethane, being nonpolar, has weaker intermolecular forces, and so it boils at a much lower temperature than the formaldehyde does, because the formaldehyde is stickier. The molecules stick to each other more. And so you have to get them moving faster before they can break free. Does that make sense? Polarity is very important in talking about miscibility. That's a funny word that scientists use, miscibility. It's like mixability, which is not a word, but they kind of sound the same and they sort of mean the same thing too. Do they mix? Refers to liquids. Liquids mixing. We talked real briefly about how oil and water don't mix, and it's because the water molecules are sticking together. The illustration was the magnetic marbles versus the glass marbles. So the water is very attracted to the other water molecules, and the oil is not. Oil is nonpolar, water is polar. And now we know the names of those forces of attraction. So the water has dipole-dipole forces, whereas the oil does not. And just kind of a saying that we have is like dissolves like. Meaning polar things are likely to dissolve in each other or be miscible. Nonpolar things are likely to be miscible in other nonpolar things. But if you get polar and nonpolar, they're not going to mix very well. Sorry, I must have eaten frogs. Which molecules have dipole-dipole forces? So we've talked about dispersion forces and dipole-dipole forces. Everything has dispersion forces. What kind of things have dipole-dipole forces? Polar. So we need to decide if these are polar or not. Now I wrote the name here because that looks like Cl4, but that wouldn't work. It's actually Ci4. So Ci4, to predict whether it's polar or not, you really kind of need to look at a Lewis structure. And we've learned how to do that, so I'm not going to review that right now. But there's a Lewis structure for carbon tetraiodide. Polar or nonpolar? What are we looking for? A polar molecule is going to have one end that's different than the other. If we look at this, we see that there are 4 electron groups around the central atom. What's the geometry? What's the shape of the molecule? It's tetrahedral, right? So it's symmetrical, and all of the atoms that are bonded to the central atom are the same. My rules of thumb, you look at the middle, you see, okay, there's no lone pairs. That's the first one. And all of these are the same. They all have the same electronegativity. That means this is a nonpolar molecule. So if this is nonpolar, does it have dipole-dipole forces? No. So that's a no. How about this one, CH3Cl? Well, you really just kind of have to sketch out the Lewis structure. There's the Lewis structure for that. Is it polar or nonpolar? It's polar. There are no lone pairs on the central atom. The lone pairs always make things lopsided. Always. There's no lone pairs, so that would suggest that it would be nonpolar, but this chlorine atom is different than the hydrogens. And if we just look at trends of electronegativity in the periodic table, we're going to expect that chlorine is more electronegative than hydrogen. And so this one's going to be lopsided. It's going to be polar. All polar molecules have dipole-dipole forces. So this is a yes. Well, okay, it's a really big yes. How about HCl? Does it have dipole-dipole forces? Yes. Yes, it does. HCl is a diatomic molecule, just two atoms. The two atoms in that molecule are different. That means that the bond is polar, the molecule has to be polar. And since it's polar, yes, it has dipole-dipole forces. So that whole business we did about the Lewis structures and Vesper theory and the shapes is important for predicting polarity of molecules and for understanding what kind of intermolecular forces they have. Any questions? Another type of intermolecular force is known as hydrogen bonding. I think of this as sort of a super dipole-dipole force. Dipole-dipole force on steroids, right? Pumped up big, strong, extra strong. The name can be a little confusing sometimes. A hydrogen bond is not a chemical bond. It's an intermolecular force. So don't get it confused with actual bonds. These are found in polar molecules that have hydrogen bonded to fluorine, oxygen, or nitrogen. Those are the three most electronegative elements, right? Fluorine's up there, oxygen and nitrogen. Those are the big three in electronegativity. That means that a hydrogen fluorine, hydrogen oxygen, or hydrogen nitrogen bond is going to be getting all choked up about this, is going to be especially polar. These forces are stronger because the partial charges are unusually large. So when we have hydrogen bonded to one of these more electronegative elements, we get stronger interactions because the delta negative and delta positive are just plain larger. They're still not even +1 and -1, but maybe they're 2/3 positive and 2/3 negative instead of 1/3 positive and 1/3 negative. And so the larger charge gives us a larger force of attraction. So we need to be able to remember the criteria for something that has hydrogen bonding. Remember the movie E.T.? E.T., phone home. Phone home. Fluorine, oxygen, or nitrogen bonded to hydrogen. So E.T., phone home, polar molecule, you've got hydrogen bonding. I know it's really dumb, but you're going to remember that. Let's look at hydrogen bonding in ethanol. So ethanol, we've got oxygen-hydrogen bonds. So this bond is especially polar. And here's a neighboring ethanol molecule, hydrogen-oxygen bond. The hydrogen of one of those is attracted to the oxygen of the neighboring one, and that's the hydrogen bond. This happens in water. So water is all hydrogen-oxygen bonds, right? And so we get this force of attraction between the hydrogen on one molecule and the oxygen on the other molecule. It always involves hydrogen. But these are forces of attraction between molecules. So hydrogen bonds between molecules, chemical bonds between atoms inside of a molecule. These hydrogen bonds are 2 to 5% as strong as a covalent bond. Even though they are a very strong intermolecular force, they're very weak compared to covalent bonds. And we observe that compounds with hydrogen bonding have higher melting and boiling points. If we compare ethanol with dimethyl ether, again, the molar masses are actually identical because these are isomers. They have the same number of carbons, the same number of hydrogens, the same number of oxygens. But the way that dimethyl ether is assembled, there is no bond between the oxygen and the hydrogen. It's not necessarily clear from that, but dimethyl ether looks like this. So, oh, I do, sorry. That's not even a, yeah. Let's start over. That was something else. That was a ketone. Yeah, it's not even an ether. There we go. So here we have, there is an oxygen in here, but it's bonded to carbons only. There's no carbon-oxygen bond. Whereas in the ethanol, same atoms, but they're arranged differently. So here we have the oxygen-hydrogen bond. And when we compare their boiling points, ethanol boils at 78 degrees, dimethyl ether boils at minus 22. The difference in boiling points is due to the presence of hydrogen bonding. Higher temperature, stronger intermolecular forces. Any questions? Water actually has a crazy high boiling point for its size. So what is this graph? This is boiling point versus molar mass. And we're comparing the group 6A hydrides and the group 4A hydrides. So oxygen, sulfur, selenium, and tellurium are all in group 4A. That's group 6A. Oh. Okay, I'm like, that is what? That's not right. No, it isn't. It isn't right. Okay. Oh, we found another mistake in the textbook. They're all in group 6A. They form compounds with hydrogen. And if we graph their boiling points, we see a nice trend here with tellurium and selenium and sulfur, that as the molar mass of the compound is getting lower, the boiling point gets lower. The dispersion forces get weaker with smaller molecules because it's harder to push around their electrons. What would we expect water to be? Well, we expect there to be a line here. It looks like there's a definite trend going on here. We expect water to be down here around minus 100 degrees Celsius. We see this trend with the group 4As, tin, germanium, silicon, and carbon. The carbon one actually drops lower than we would expect. We'd expect it to be up here. Why is water way up there? What does water have that the other compounds in that group do not have? Hydrogen bonding. Hydrogen bonding is a very strong intermolecular force. And so that causes the boiling point of water to be 100 degrees. If it were not for hydrogen bonding, life would not exist, because there would be no water to drink. It would all be frozen. Our bodies are mostly composed of water, and so just nothing would work without hydrogen bonding. Hydrogen bonding is awesome. Okay, we should be able to answer questions like this. Which has the higher boiling point, HF or HCl, and why? The why is really important because you've got a 50% chance of guessing correctly, right? So we got to take the guessing out and just understand why. Well, what affects boiling point? Intermolecular forces, right? So let's look at these two guys. We've got HF, we've got HCl, two very simple diatomic molecules. They both have dispersion forces, right? Are they both polar? They are. So they both have dipole-dipole forces. What about hydrogen bonding? Do they both have hydrogen bonding? No. HF has hydrogen bonding. ET, phone home, F and H. So this one has hydrogen bonding. In addition to the other dipole-dipole and the dispersion forces. Question?
Does the greater difference in the question is it between hydrogen and fluorine than hydrogen and fluorine playing into it too?
Yeah, chlorine is less electronegative than fluorine. It also has to do with the size. Because oxygen and chlorine are similar actually in electronegativity, but oxygen is much smaller. And with the smaller atom, then they can get closer together. So it's not only a charge difference with the hydrogen bonding, it also has to do with the size of the atom. So because fluorine is a smaller atom than chlorine, they can get closer to each other when they do the hydrogen bonding, and it's stronger. Dispersion forces would be larger for the hydrogen chloride, but dispersion forces are very weak. And so when you're comparing differences between intermolecular forces, you want to look at the strongest one first. So the strongest one is the hydrogen bonding. Hydrogen fluoride has hydrogen bonding. Hydrogen chloride does not. So having hydrogen bonding, is that going to make the boiling point higher or lower? Higher. So we're going to expect HF to have the higher boiling point because it has hydrogen bonding and the HCl does not. That added attraction means that in order to get that substance to boil, you have to give it more kinetic energy. It needs more kinetic energy to overcome the stronger forces. That makes sense? The last force is ion-dipole force. This doesn't happen in a compound. Hydrogen bonding happens in a pure substance, like ethanol or water. Ion-dipole forces only occur in mixtures, when you have an ionic compound mixed with a polar compound. And this is very important in the formation of aqueous solutions. And it's actually the strongest type of intermolecular force. So when we dissolve sodium chloride in water, it's the ion-dipole force that allows it to dissolve. The ion-dipole force is an interaction between a dipole in the covalent compound with an actual ion. And it makes sense that this force is stronger because now one of these substances actually has a full positive or negative charge. And it might even be +2 or +3 or -2. Whereas the charges on the water are partial charges. So we've got this force of attraction. The water, being polar, has a positive end. It can turn towards the chloride, the negative ion, and the negative end will be attracted to the positive ion. And so we have these ion-dipole forces occurring between polar compounds and ionic compounds. So there's a summary of intermolecular forces. You need to know their names, what kind of substances that they're present in, and their relative strengths. So all of that is listed out there. Hydrogen bonding is very important in DNA. Your DNA is what carries the genetic information for who you are, and all of your cells have DNA in them. DNA is composed of 2 strands, and what holds the 2 strands together is hydrogen bonds. So there are 2 different types of bases. Thymine and adenine each have, thymine and adenine can bond with 2 hydrogen bonds, and cytosine and guanine have 3 groups that can bond with hydrogen bonds. And so the hydrogen bonding enables these things to pair up. Cytosine will never pair up with adenine. It doesn't match up right because he only has 2, and this one has 3. And so these base pairs match up because of the number of hydrogen bonds that they can form with each other. And so what happens with your DNA is that you have these 2 strands and they are matched to each other. They're complementary. If one has thymine in that position on the other side, there's adenine. And when it replicates, the strand separates and new pairs are brought in that match up the old strand. And so you end up with 2 strands that are identical to the original strand, and it's all due to hydrogen bonding. And of course, the details of DNA replication are a topic for biochemistry, which is also very interesting.